Okay, my presentation is on 3D object manipulation in a single photograph. So here is an on the right side we have a photograph. So for example, there's a taxi, and we can actually select in this paper, and they have mentioned a way to actually select the taxi and make 3D manipulation, like rotate the taxi over, or maybe scale the taxi in 3D domain, and so on. For example, in the lower photograph, we can see that the taxi has been flipped over. So yes, in this paper, the author has talked about that, like how they have achieved this. So for example, we have Photoshop Photoshop and other image softwares can control the image pixels in 2D domain. But in this paper, the authors have discussed how to manipulate objects in 3D domain. So for example, by doing this, we can expose the hidden parts of an object in 3D domain. For example, in the original image, the lower part or the back part of the taxi was not exposed, but when we have flipped the car over, and then we can also see the bottom part of the car. So we have already achieved success with editing 2D image like Photoshop, and the Photoshop is quite popular, and it has become like a legitimate English verb. So in this paper, they have talked about how to perform 3D manipulators, but they want to perform it like the conveniency of the Photoshop application. So the way to they have achieved this is by using stock 3D models, and there are a lot of 3D models available that are used publicly. So they have used those repositories of 3D models to achieve this result. So for example, here's an image of a chair flipped over on its back, and the authors showed how they selected the chair from the image and perform a 3D operation, that is the rotation of the chair. And by rotating the chair, it has also revealed some of its hidden part. And in the third image, we can see that the chair was flipped over and it is on its side, like the other side. And yes, like we can they have shown like how to manipulate objects in 3D domain. So there were some challenges in this, like there was geometry mismatch and appearance mismatch and illumination mismatch. So what geometry mismatch was that though the repository that are for the 3D models can be pretty large, but the standard, even among the standard household items like detergent bottles, there are geometric variances. Like if we select a chair, there can be no chair in the repository that is the exact match of this chair in the image. Also for natural examples like a tree or banana, it is certain that the geometry would vary. So in those cases, we need to they have like come up with some interface that allows the user to actually correct the geometry geometric errors and correct those errors so that the geometry would match with the object. And there's also appearance mismatch, because the whatever we may have on the repository, like on the 3D models, the appearance might not like the geometry would match, like the chair might that the geometry of the chair might exactly match, but the color or the texture might not match. So that is, they are calling the appearance mismatch. And the illumination mismatch is because of the in the original image, there is some illumination by the light in the environment. So when we're manipulating the 3D object in the image, we have to also remain the consistent illumination in the environment like the original image was. So that's the illumination mismatch. So how the challenges were overcome. So the author uses the pixel information in the visible parts of the object. So like we have some sort of visible part in the image that corresponds to the 3D model in the in the public repository. So authors used those information in the pixels and also the geometry of the 3D model to overcome these issues. Also, for the geometric error, the authors proposed and designed an interface that allows the user to align the 3D model into the 2D image so that so that the geometric error can be solved. And also for the illumination, and they follow the Lambertian illumination. So for now they ignored the the reflections and inter-object interactions for now. So the author's key contribution was an approach that allows the user to manipulate the 3D objects out of the 2D plane and manipulate the objects in 3D. To do so, the actually um, actually the authors has used the symmetries in object like the symmetry that are present in the 3D model. And for example, in the 2D image there are some hidden parts that are not present. So for those parts, and they have used symmetries and also an algorithm called patch match algorithm. So by using that, they were successful to reveal the hidden parts. And also they have made no assumptions about the nature of the structure of the object that is being manipulated by the user. So in this paper, they have the authors have assumed a Lambertian model of illumination. That is, there is no reflection or specular light reflection or surface scattering or interreflection among the objects. So how they have implemented this system is that for the image manipulation, a photograph is initially taken, and for example, I want to manipulate the chair. So a 3D model of the chair is taken from an online repository, like a public online 3D model repository, and then the user and there is an interface that allows the user to align the model to the photograph that is present. And then after the model has been aligned to the photograph, then the user can perform any 3D operations that he likes, and the image is updated like that. And during this operation, like when the user is performing the 3D manipulation, the reveal there are some hidden parts of the object, like the backside of a chair, and that might be hidden in the original image, but that gets revealed in the manipulation. And this their system automatically estimates the environment illumination and reflectance, and at last they tried to come up with the illumination model and the appearance to obtain the final photograph. So here was the implementation. Like this is the photo they mentioned they have put on the paper. So there's this original photograph of this chair lying on its back, and we want to manipulate the chair in this image. So for that, we have selected a stock 3D model of the chair from an online repository, and then user selects a mask. In the mask, we can see that only the object, like the object of interest, are taken, and the background and other objects are grayed out. So in the mask, we can see that the pixels that we are not interested in are given in gray or black, and the object that we're interested in, that is given in white. So this after this, the user actually perform the geometric correction, and after the geometric correction is done, then we can manipulate the 3D object in any way the user likes. And after that, like the system can estimate the illumination of the environment, and by that we can see that from the model we have some hidden parts that were hidden in the original image, but that is revealed here in the green parts. So these green parts were not in the original image, but from the model and from their system, like they have estimated these hidden parts, and they have completed the final result is shown here. So the 3D model can be downloaded from any available public repository, like visiting turbosquid.com, and like this is the textual like algorithm for what we have seen in the image. Like then the user completes a mask for object pixels, and then we are using a patch match algorithm to paint the background. And for complex background, the user may touch up the background after in painting. So if the object's initial pose was something like theta, and so after the transformation, the pose gets changed, so it becomes omega. So the author have modeled the initial image as the function of the pose of the object, and also the object appearance and independent illumination. So that is we can if the original image was I, we can say that this is the function of the original image pose, that is theta, and the object geometry, which is x, and the appearance is t, and the illumination is L. And if J is the final image, so the illumination should be the same. So that's why where the illumination model is the same L, but the object geometry is changed, that is unknown, and object appearance is also changed. So I have marked it with T1, and the infrared illumination is the same, that is L. So we have J, which is a function of omega, x1, T1, and L. So for geometry correction, so as we already know that there are three types of challenges in this system. So the first one is geometry correction. So the authors have provided a user-guided approach, the way a user can correct the geometry of the 3D model to match with the photographed object. So basically what the user does is he sets a 3D to 2D correspondence in the photograph by dragging points and matching points with 3D model and 2D images. And the authors have used something called EPNP algorithm to estimate the pose of the model that is in the photograph. And the algorithm takes the points that has been specified by the user and the camera parameters. So for the camera parameters, the authors mentioned that they tried to read the EXIF tags, that is the focal length, skew, and pixel aspect ratio. And if that is not present in the image, they take some default values to assume the camera parameters. So here's the interface. So in here we can see that there is a 3D model of a banana, and there is a real banana in the image. So the user tries to align the 3D model with the banana by clicking on the model and aligning the different points of banana. So this is the way the user can correct the geometry correction. For the illumination, the system assumes that there's a Lambertian illumination. So Lambertian illumination model does not take into any reflection or refraction elements. It also doesn't compute any speculation. There is only a matte or diffusely reflecting surface. So the system is assuming that. And for appearance estimation, so for example, there are some hidden parts in the image that we cannot see, but the hidden part is present in the 3D model. So for to reveal those hidden parts, and the authors have used a Markov random field over the object. So at first iteration, so there is some image and we can see some face of the object. And so for the first iteration, there is a bilateral plane, and over the bilateral plane, by using the MRF, we can actually I mean, the authors have actually calculates what is the other side of the plane, that is the layer 2. So layer 1 is the part that we can see on the image, and layer 2 is the part that we cannot see on the image, that is the back side. And so, and we take another plane that is that can be any plane, and from that we compute the layer 3 using the I mean, to compute layer 3, we need the MRF and also the layer 1. So from layer 1, we compute layer 3, and from layer 2, we compute layer 4, and so on. So the authors have found out that if they use 6 iterations of this algorithm, then they get the perfect result. So here are some final results. So for example, they have used some of the images and to manipulate 3D objects. For example, in the second row, we can see that there was a car that was on a plain plain field, and there was a cliff there. So they have manipulated the image to make the car cliffing by hanging on a cliff. And also there is a photo of a hat, and by manipulating 3D in 3D domain, the authors managed to scale the hat, the size of the hat, and also make it rotate. And also this is an image from World War II that we can see many planes, and the authors manipulated this image and made the planes face the other way. So for the evaluation, the authors have used three types of evaluation. That is a geometric evaluation, illumination evaluation, and geometric correction timings. So for example, geometric evaluation, that is they have uh, as the user is being presented with an interface that allows them to correct the or align the 3D model with the image. So we can say that the user can accurately correct the geometry to match the photoshopped objects, I mean photographed objects. So they have compared their result with the other papers like Zhu et al. For photographs of crane, taxi cab, and banana. So in this image, we're only seeing the example of chair, and they have shown that their result is the best from the other one, because basically user is correcting the geometry data. So the if the user has enough time, then he can actually align the 3D model with the photograph completely. So for the illumination evaluation, so the author took 12 pictures of the chair on the ground, and they have used that as a ground truth photographs, and from that they have calculated the mean squared error for three models, and in this image we can see that we can see the graph of the mean squared error for three algorithms. I mean there are 5 algorithms, and their one is the one in the cyan color or the green color. So we can see that the MSC error of the authors of this paper is very low. And geometry correction timing, so they had 4 users, and the 4 users are given like different objects or different models to align the photographs with the 3D models, and they calculated like how much time the user needed um, to do the geometry calculation or geometry fix the geometry errors in the model. So they found out that it was directly related to the complexity of the model. For example, the chair has many points or many meshes in the 3D model, so it took the user most of the time to do the chair and also the crane. And we can see that the least time was in Mango, because a Mango is pretty uh, it has pretty less meshes other than the like compared with chair or crane. So in this paper, the author have presented and way to perform 3D manipulations on photograph. So, but for example, if we want to manipulate a 3D object in a scene, we don't have to do it by hand or going to the scene. We can just take the picture and manipulate the 3D objects by 3D manipulation using this system. And using this approach, any artist like movie artist or the animation can be made. So using their approach, and they have also there's also a video on YouTube that they have shown that using their system they have made a paper bird fly in their hands. So there is also a video of that. And while the authors use their approach to improve the experience of editing photographs, it can also be used to like removing errors and like correcting the models that are present in the 3D public repositories. So thank you. That was my paper. Any question?